Hello, everyone, and welcome to this Smiths Interconnect webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenter and go over today's agenda. So with us today, we have Tim Meehan. Tim is a technical application engineer of fiber optics and RF components at Smiths Interconnect. To read more about him, we have his bio listed in the speaker window. And now let's go over today's agenda. So first, we're going to discuss the need for passive temperature compensation. We're going to understand the digital active solutions versus passive. We will address environmental factors that influence temperature compensation. And we're going to analyze actual applications on how temperature compensation works in RF circuit designs. Then we will have a brief Q&A session. And with that, I will pass things over to Tim so that he can get us started. Tim, go right ahead.
Thank you, Katie. I'm going to be giving a couple of real-world examples for selecting our passive temperature compensation in RF circuits, but I thought we'd take a minute just to discuss active versus passive circuits. This may be very simple for many people on this webinar, but I thought I would just take a minute. Basically, an active circuit is a component or a circuit that requires a voltage to operate. These active components, they produce energy in the form of voltage or current, where a passive component does not. It does not consume energy. It's typically made up of resistors, attenuators, capacitors, and the like. One thing significant with active versus passive circuits is basically the mean time between failure, the MTBF, or some people refer to it as FIT rate, which is failure in time. Per Mill Handbook 217, you can see that the resistors are going to be more reliable than active when using a passive circuit. And I'm going to introduce the thermopad and the advantage of the thermopad. A thermopad is a passive device that we use for temperature compensation in our circuits, primarily with power amplifiers, up converters, down converters. With a singular thermopad device, like you can see down in the diagram on the left, we can accomplish by using just one simple passive component to accomplish what is happening on the active side. So a couple examples. We're going to look at a couple of amplifiers, a 30 dB gallium arsenide, and we're going to look at a gallium nitride 20 dB. So this example here is for the 30 dB amplifier. The chart on the left is showing what the gain loss is over temperature for this amplifier, where we're trying to keep a 30 dB type of gain, and we want it to be linear across. When we add the thermopad in series with this amplifier, the compensated attenuation, as you can see on the chart on the right, gives a much flatter response and gives approximately about 24 dB flat across response. Now, how did we get to using this 3 dB attenuator with a -9 compensation? Is we start by using what we call our thermopad selector tool. By using this thermopad selector tool, we can look at different various thermopads that we offer, different attenuation sizes, depending on what frequency, whether we're looking for wire bond or a solder type of application. For this particular application, one of our major customers is using a component is what is called our MTVA size, and the frequency they're using is at 8 gigahertz, which is within the allowable frequency range of our MTVA product line. So by selecting the 3 dB MTVA -9, you see it pictured down in the left-hand corner, from our thermopad selector tool, it gives what the amplifier gain is in conjunction using the thermopad and the compensated attenuation. It also gives some specifications about the component, a quick summary of what the frequency is, the sizes, power handling, operating temperature. And there's also a few links in the ThermoPad tool, which we'll go over later on as well. This is one of the outputs from a ThermoPad tool. We can click on printing out a sheet that gives all of the specifics needed for this ThermoPad that engineers can take away and give their procurement people and tell them this is a component that we need for our circuit, and this is the responses that we will be able to expect. On the left-hand side is the ThermoPad. On the right is the amplifier response when you add in the ThermoPad. And this is just a typical wire bond component installation. The component would be epoxied to the circuit board with either a wire or ribbon bond attaching to the input and the outputs to the transmission lines of the circuit. Next example we have is a gallium nitride 20 dB amplifier, where we're going to be using a 2 dB attenuator with a compensation of -4. The chart on the left shows the gain loss over temperature for this 20 dB amplifier. And then we put the ThermoPad in series with that amplifier. The chart on the right shows the compensation with the ThermoPad. As you can see, it's a nice linear response for a clean signal. And again, we go back to our ThermoPad tool. We're going to take and again consider what frequency the customer's looking at, whether we're going to be solderable or a wire bond type of application. For this customer, they were using a component that is our temperature variable size, and they're looking for a solderable application, and they're looking at 2.4 gigahertz, which is within the acceptable frequency range of the ThermoPad. So by selecting the 2-4, you can see it pictured on the left-hand side in our ThermoPad selector tool. We get our specifications, tells us our sizes, again, our power, operating temperature, what type of resistive material we're using. And again, the output from the ThermoPad tool with all the details that can be printed or emailed. Again, the ThermoPad response is on the left. The amplifier, in conjunction with the ThermoPad, we get that green line, which shows a much nicer linear line. And here's an example of just a typical surface mount type of connection. You see the component is soldered down. This type of component has an edge wrap, so you see a nice solder fillet during the installation. Not all components have edge wraps though. Some are just flip chips, so you won't see that nice solder fillet. Some of those components allow for higher frequency because some capacitance is generated from some of those edge wraps. So not all of these components will have those edge wraps, depending on the application and the product type. And now we're going to share a short demo. We'll present it on how to find and use the ThermoPad selector tool.
During the presentation, I've shown a few screenshots of our ThermoPad selector tool, and I'm going to take a few minutes to show you where you can find it on our website. You can find it by going to smithsinterconnect.com. By going to products, we select RFMW components, and we select resistive components. From there, we scroll down to the ThermoPad configurator, which has a link conveniently located on our main page. From the ThermoPad selector tool, I'll just randomly select a component. And this is from our WTVA family, a 3dB -7. From there, we get our visual of our ThermoPad response and what the amplifier response is going to look like after the ThermoPad is used to compensate for the temperature change in the amplifier. There's a quick reference to the specifications with also pictures of the components as well. We have some links to application notes. For application notes, there's more information about the ThermoPad temperature compensation. And then we also have another application note for attenuation shift due to self-heating. Since these components are temperature variable, when they are power applied to them, they will change values. Also, for each of our product series is a product brochure, which has a link to it where you can find out more details about the part type, more specifics about the electrical, environmental, mechanical specifications, also about derating, mechanical drawings with tolerances, as well as suggested mounting footprints and how to order them. There's also a temperature reference guide, which shows tabulated data, similar to what you see in the graphs. And also from the presentation, I had some screenshots from this print chart, which is a nice link to print out exactly what we're looking at, the WTVA 3dB -7. It has all the specifications and the expected ThermoPad response, as well as the amplifier response in one simple page to print out. Now, if the ThermoPad, the WTVA series, is something that might not be the right form, fit, or function, you can return to the top, where you can select any of the different family types we have listed. I'll go ahead and select our TVA and select randomly another one. This is a 1dB -7. Again, we have a quick reference to the specifications, pictures of what the components look like, as well as the application notes I just showed. It has its own brochure. Again, goes into more detail about the specifics of this series, the technical characteristics, including electrical, environmental, mechanical, as well as the typical data, mechanical drawings with tolerances, and also suggested mounting footprints and how to order these components. Lastly, again, you can print out the chart so you have one single page that has the component we were looking at with the specifications, the ThermoPad response, as well as the amplifier response, all on one convenient page.
All right, now I'd like to discuss something called temperature compensation compression. I think this is important to touch on. So temperature compensation compression, the ThermoPad tool we were just looking at, all of the calculations are made at DC, which right now we're talking about RF circuits, so DC doesn't help very much. When these components were first introduced back in the 90s, patented back in 1994, the frequencies we were using were much lower, around 2.4 gigahertz, what these were designed for. And a DC to 2 gigahertz, it's almost a one-to-one comparison for temperature compensation. As we get into higher frequencies, you can see on the chart on the left, what the shift is it's compressing. We're not getting as much shift as we expect. If we're going to be using these components out to, say, 20 gigahertz, where this component should be like a -7, we're only getting about a -3 type of compensation. And again, at 9 gigahertz, if we're looking for a component that's going to give us about a -5 compensation, we're going to have to use a component closer to probably a -7. Since these components have been developed very long ago, decades ago, we've created new components to address this situation, and that is what the K2 TVA is. The K2 TVA is a second generation type of ThermoPad, and what that does is gives true compensation within frequency bands, as you can see by the upper and lower limits on the chart on the right. At the higher frequencies, we are seeing the expected performance for this compensation. These K2 TVAs are band limited. They're not broadband, so I know several of our customers continue to use the wider band components and just put multiple thermal pads in series to deal with this phenomenon. We have S parameters, though, that can help design engineers with our customers. And we can use these S parameters to see how these components work at frequencies. We have a partner with Monolithics. It's a third party that takes our components. They characterize them with different substrates to show and create models on what to expect for our park's performance. Again, it's a third party. We have our own S parameters we also publish on our website. And then we have another partner that we work with, X Microwave. They use our components, they take them, they characterize them, and they actually develop fixtures and jigs that customers can use and create almost like their own circuits in their own type of applications to sort of replicate what they would expect to see in their own test environments. And with that, I think we're going to get into the question and answer portion of this presentation.
All right, Tim, thank you so much for the presentation and for showing us that demo. So we have a couple questions in our queue here that have come in from our attendees. All right, Tim, so I'm just going to go through as many of these as we can. The first one here, when considering temperature comp, does it matter if the application is wire bondable or solderable?
That's a good question, Katie. Thank you for asking that. No, temp comp is the same for both. It doesn't matter whether it's wire bondable or whether it's solderable, and that's actually why you don't see a selection for that in the ThermoPad tool.
Okay, thank you so much for that answer. All right, next one here. How long has passive temp comp been available?
It's existed probably for over 30 years. Like I was saying earlier, we started with lower frequencies, and over the years, we've developed other types, wideband ones, the second generation K2 TVA I just showed you. That's probably been out for a couple of years now.
All right, thank you so much. Next one here. Are temp comp components tested for their functionality?
That's another good question. We get that asked often by our customers. Yes, we do. We have our what we call our COTS procs or our COTS parts, which are just our standard off-the-shelf parts, where we do a sample test where we show conformance to the expected temperature compensation. And then we have high-rel versions where we actually supply data packages that show the actual performance of the components over temperature.
All right, next one here. Do you make products for 150C or 175C operation?
We can. That is outside the normal operating temperature components, but we do have special designs that we do customize for our customers.
Okay, thank you so much. And this is the last one we have in the queue today. Are there thermopods available for KU and KA bands? If yes, can you please share some part numbers?
Yes, that would be the KTVA series as well as the K2 TVA series. Those would be the two different product series they would want to look at. And again, they would need to just let us know what frequencies, what sizes they're looking for, and whether it's solderable or wire bondable.
So let's do this last one.
All right.
Can you have a thermopod selector tool where I just enter my amplifier gain at different temperatures, then the tool suggests to me the suitable part number?
And that's sort of a backwards way of approaching our ThermoPad tool. You sort of need to know how your amplifier gain is, and therefore you can find which ThermoPad you want to go to. You may have to select a couple of different variations, but I think the ThermoPad tool will get you in the ballpark where you need to be, and then you can just select the different types, whether, dB value and shift, and then you can see how it will compensate for you.
All right, Tim, thank you so much for that last answer. So those are all the questions in our queue today. So let's start to wrap things up here. I want to say a huge thank you, Tim, to you for giving a good presentation and for sharing that demo with us. It was a pleasure to have you.
Thank you, Katie. I appreciate all your support.
Thank you all for attending today's webinar. Take care, and we will speak with all of you soon.